unpredictable natural disasters, capable of reshaping entire landscapes and causing devastating damage within seconds. These events occur due to the movement of tectonic plates, which are massive sections of the Earth's crust that slowly shift over time. As these plates interact, stress builds up along faults, and when the stress surpasses a critical threshold, it is released in the form of seismic waves, resulting in an earthquake. This sudden energy release can have catastrophic consequences, from the collapse of buildings to massive landslides and even tsunamis. Understanding how earthquakes are measured is crucial for assessing their potential impact, improving safety measures, and developing early warning systems. Scientists have developed different methods to quantify earthquakes, with the most well-known being the Richter scale, the moment magnitude scale, and the Mercalli intensity scale. Each of these scales serves a different purpose, providing insight into either the total energy released by an earthquake or the effects experienced on the Earth's surface. The Richter scale, first introduced in 1935 by seismologist Charles F. Richter, was the original method for quantifying earthquake magnitude. It is a logarithmic scale, meaning that each whole number increase represents a tenfold increase in the amplitude of seismic waves and approximately 32 times more energy release. For example, an earthquake measuring 6.0 on the Richter scale is 10 times more powerful in terms of ground motion than a 5.0 and releases 32 times more energy. Similarly, a 7.0 earthquake is 1,000 times stronger than a 4.0, demonstrating how destructive high-magnitude earthquakes can be. However, the Richter scale had its limitations, particularly for large earthquakes and those occurring in different regions of the world. It was originally designed to measure earthquakes in California using a specific type of seismometer, which meant that its accuracy diminished for extremely powerful quakes or those occurring far from California. Due to these limitations, modern seismologists now use the moment magnitude scale, which provides a more accurate and standardized measurement of earthquake magnitude across the globe. Unlike the Richter scale, which is based on the amplitude of seismic waves, the moment magnitude scale considers additional factors such as the size of the fault rupture, the amount of slip along the fault, and the type of rock involved. This allows for a more precise measurement of an earthquake's total energy, especially for those exceeding magnitude 7.0. Today, the moment magnitude scale is the preferred method for reporting earthquake magnitudes, as it provides consistency across different locations and is not limited by the same constraints as the Richter scale. While the Richter and moment magnitude scales measure the energy release of an earthquake, they do not indicate how strongly an earthquake is felt or how much damage it causes at the surface. For this purpose, scientists and emergency responders use the Mercalli intensity scale, which classifies earthquakes based on their observable effects on people, buildings, and landscapes. Developed by Giuseppe Mercalli in the late 19th century, this scale consists of 12 levels, ranging from 1, where an earthquake is barely perceptible, to 12, where total destruction occurs. Unlike magnitude scales, which remain constant regardless of location, Mercalli intensity depends on several factors, including distance from the epicenter, local geology, and building construction quality. An earthquake with a magnitude of 6.0 might have an intensity level of 14 to 5 in one location but 8 to 9 in another, depending on these factors. For example, an earthquake striking a city with poorly constructed buildings on soft soil may cause severe damage, while the same earthquake occurring in a rural area with buildings on solid bedrock might have a much lower impact. This makes the Mercalli scale particularly useful for assessing damage and guiding emergency response efforts in affected regions. In addition to magnitude and intensity, the depth of an earthquake also plays a critical role in determining its impact. Earthquakes can be classified into three categories based on depth: shallow, 0 to 70 kilometers, intermediate, 70 to 300 kilometers, and deep, 300 to 700 kilometers. Shallow earthquakes are typically the most destructive because their seismic waves reach the surface with high energy. The 2011 Tohoku earthquake in Japan, which had a magnitude of 9.1, was a shallow earthquake and caused immense destruction, including a powerful tsunami that devastated coastal areas. In contrast, the 2013 Okhotsk earthquake, which had a magnitude of 8.3, occurred at a depth of over 600 kilometers and caused little surface damage despite its high magnitude. This difference highlights how deeper earthquakes tend to lose much of their energy before reaching the surface, reducing their overall impact. Another important factor influencing an earthquake's effects is the geological characteristics of the affected area. Certain types of soil and rock can amplify seismic waves, making an earthquake more destructive than it would be otherwise. Loose, sandy, or water-saturated soil is particularly prone to a phenomenon called liquefaction, in which the ground temporarily behaves like a liquid, causing buildings and infrastructure to sink or collapse. In contrast, bedrock is more stable and helps absorb seismic energy, reducing damage. This explains why some earthquakes of moderate magnitude can cause extreme destruction in one location but minimal damage in another. Earthquakes vary greatly in size, ranging from tiny tremors that go unnoticed to massive seismic events that shake entire continents. Earthquakes below magnitude 3.0 are typically imperceptible to humans and are only detected by sensitive instruments. Those between 3.0 and 4.9 can be felt but rarely cause damage, while earthquakes between 5.0 and 6.9 can cause moderate to severe structural damage, particularly in populated areas. Earthquakes of magnitude 7.0 and above are classified as major and can result in widespread destruction, while those exceeding magnitude 9.0 are considered catastrophic. The largest earthquake ever recorded was the 1960 Valdivia earthquake in Chile, which had a magnitude of 9.5 and generated tsunamis up to 25 meters high. Other notable high-magnitude earthquakes include the 2004 Indian Ocean earthquake, which had a magnitude between 9.1 and 9.3 and triggered a massive tsunami that killed over 230,000 people, and the 2011 Japan earthquake, which caused the Fukushima nuclear disaster. A common question is whether an earthquake could ever reach a magnitude of 10.0 or higher. While theoretically possible, such an event is highly unlikely. An earthquake of magnitude 10.0 would require a fault rupture extending thousands of kilometers. The largest known fault lines, such as the San Andreas Fault in California and the subduction zones in the Pacific, are capable of generating earthquakes above magnitude 9.0, but there is no evidence that they could produce a 10.0 earthquake. Some scientists speculate that if an entire tectonic plate boundary were to rupture, a magnitude 10.0 or higher earthquake could occur, but no known faults on Earth are large enough to sustain such an event. Despite the unpredictability of earthquakes, advances in seismology and early warning systems have helped mitigate their impact. Networks of seismometers detect seismic activity and can provide alerts seconds to minutes before shaking reaches populated areas, allowing people to take cover, and automatic systems to shut down critical infrastructure such as gas lines and power plants. While earthquakes cannot be prevented, continued research and improvements in building design, emergency preparedness, and early warning systems can help reduce casualties and damage in seismically active regions. Understanding how earthquakes are measured and what influences their impact is essential for developing better strategies to protect lives and infrastructure in the face of these powerful natural events.